The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Alrighty, so we're back. We're going to do the examples for the we just sort of described in the previous notes. And again, once again, these are in the, if you have your DFORM directory here, they're in the examples, applications, BioBlast. This shows you the two programs we're going to run. We just have two examples. And then we're going to be comparing two pieces of actual data. So if you look at this, this shows you, what that data looks like. So sequence ID and then very long sequences here. And not all, it'd be sure nice if they were all the same length, but they certainly are not the same length. They vary dramatically here. You can see, there's probably one that's, yeah, look at that guy. What's he doing? Super long. So this is a reference bacteria data set. This is known data, and this is a sequence here of some data taken from somebody's palm. And this is open source data, not, and so yeah. So this is just an example of that. And so you can imagine one would want to do a comparison of the data, of what the DNA sequences on of bacteria on the person's hand are with some reference data set. So obviously, we are not going to be using a data set. This is a very small data set here. We're not going to be able to do, we're probably not going to, we wouldn't expect to have any matches here, and we're not going to have any, but this just shows you kind of how that works. So if we go over here, and so the first one here was this BB1. It's just basically alrighty. So what we've done is we set our word size. We're going to use 10 base pairs, so that's what we're basically dealing with 10 mers. And wrote a little program here that what it does is given a CSV file, FASTA file, and a word size, it then creates the associative array as we described. So basically each sequence will be a row. So for instance, we'll get into that. And likewise, each 10 mer will then be a column. And so we do this for the two data sets. Here is our matrix multiply. So A1 times A2 transpose gives us A1, A2. And here is our pedigreed matrix multiply, the cat key mul A1, A2 transpose, and gives us A1, A2 key. And so we can now look at that. So A1 has 198, that's the bacteria, it had 198 sequences with 8,001 unique 10 mers. A2 had 1,000 sequences with 2,365 unique 10 mers. And then when you matrix multiply them, you see that 85 of the 195 in the reference had a match with 415 of the 999 in the sample. So we're losing about half in each case because the associative array does not store empty values. There's going to be no key, which is an empty row, completely empty row or completely empty column. So we can now look at that data. So if we look at figure 1 here. So this is A1. So this shows you, again here, why don't we zoom in? Right. So that gives you a better sense of the structure. You can actually click on that. So here's a 10 mer that appears in an awful lot of things. So basically this 10-mer appears in an awful lot of things. You know, and these are examples of, you know, here's a row corresponding to a particular sequence ID. So that's A1. That's the reference. A2, the sample, pretty much the same type of thing. Although a little bit different structure, more of these dense things maybe. Why don't we zoom in on one of these blobs here? See those types of blobs there. We got this guy. Who's he? This guy begins with GCCAC and GCCTT and other types of things there. And this is the cross. So if we go now to figure 3, this is the cross correlation of all those, and it holds the count. So you can see here 1, you know, 1. Most of these are just 1, and unless I did some kind of thresholding, I probably couldn't even find the ones that were larger. And then figure 4 here is our pedigreed multiplication. So now it shows you what the actual. So this tells us that this sequence ID and this, you know, so this reference sequence ID and this sample sequence ID had a match at this 10-mer. There we go. So we go back here, and as we see, as I clicked on that, it printed out the full sequence. So if you wanted to ever like just do a cut and paste and then put this in something else. So like if I wanted to look at this row, you know, I could then do A1 and that gives me that row, you know. And I can do other things, you know, I could do like, all right, let's sum that, you know, I could sum the columns up. And that tells me there's 138 unique sequences in that sequence ID. So those types of things there. All right. So I think we pretty much covered that. Yep. And so now we'll go on to the next example. And I apologize, this takes a little bit longer to run, because now I'm doing two things when I read in the data. I'm doing the same thing I did before in terms of saying I want 10 mers, then I'm going to read the data again with a slightly different function, and it's going to return 2 associative arrays. This associative array was the same as before, which showed us the actual counts, how many times if you had a 10 mer and it counted. The next one gives us a concatenated list of the positions. So if it appeared 5 times, it will actually show us, it'll hold that information, a list of the 5 location, you know, is in the greater sequence, which then allows us to do those things I talked about before. So this takes a minute to do that. Probably with some optimization, I have no doubt that this could be made faster. And also with the video recording going on, we have a lot of pressure on this little computer. Just some additional information here in terms of the whos command. You know, so we basically did whos A to show me all the different associative arrays I have, as you can see. And this tallies up the bytes that are associated. So our first associative array, as you saw, was about 700 kilobytes. And that basically adds up all the data stored in all the data structures inside it. Usually does a pretty good job of that. Likewise, and as you can see, there's a significant reduction in the total size of that. And in this case, we didn't really add that much by adding the keys. You know, so this is a very nice data set for us to do our cat key mul on. There was no dense diagonal or anything like that to get in our way there. So that was a very useful thing to have. Well, we're on at least we're now on the second read, so almost there. And being able to click on the thing and actually print it out is because when we actually do the SPI plot, in this case it works out pretty well because our keys are relatively short. But we do truncate that. So if you have a row key or a column key that's very long, when we do the plots, we truncate that, and then you would never actually know what the true full string was. So, all right, I think we're just about finished there. All righty. So again, we read in the data, and now I wanted to make a degree distribution of the data. So just like we did our degree distributions earlier, this is a great way to get a sense of the overall statistics. All right. So I took one A1n, and the way I do that is I have the associative array A1. If I do the ADJ, or adjacency matrix thing, this basically just pops out the internal sparse matrix that's stored. Okay, and now I can do regular math on that. And we happen to have this little built-in function called outDegree, which essentially does, on the out direction, the appropriate sums and returns a sparse matrix, which we can then plot in this log-log form. So this is the reference data. You see, has this distribution here, which is very power law-like. Although, as we saw in the earliest classes, unless we properly fit and bin this, we wouldn't really know if this was a power law or something like it. But probably our first order linear fit of a power law would be at least a good place to start, as it usually is with this data. There's the other one. Would appear to be even more power law-like, but again, until we bin it, we don't really know what happens when we start binning this stuff up here. Maybe it will bow up in some way, maybe it won't. Probably it would. Probably would look more like this. A question for you, or a good question is, I showed you that other data set, and it didn't look like this. You saw a very kind of almost a log normal Gaussian distribution. And you might say, well, because it's the same data, it's still 10 mer type of data. And so the only difference is the size. And so when you have 10 mers, you have, since each one can be, you have 4 choices of letter, all right, you essentially have 2 million total possible 10 mers. So in this data set, in fact, we can count here, right? If we do, it's A1. If we do N and Z, A1, we only have 274,000 entries. So we're not fully sampling the 2 million possibilities here. In the other data set, that database was actually 500 million entries. And so we're really fully sampling. And so you're getting, this basically what's happening is, these guys are rare, they don't show up, and they start getting, more, you're hitting them once, and eventually you begin to create this sort of more Gaussian distribution look, or bell curve look, when you start fully sampling. I don't know if that's generally true or not, but one could hypothesize that a lot of the data, and this is just a guess, that a lot of the data we see as power law is because we're not fully sampling the total space that emerges, or that total space is growing at a rate as we sample it. So like domain names, we haven't fully sampled the entire space of domain names, and the set of domain names in the internet continues to grow at a fairly significant rate. Now maybe one day there will stop being new domain names, and then when we start doing our sampling, maybe our distributions on domain names won't look so power law anymore, but more like a log normal distribution with a kind of a bell shape. Just a hypothesis, but certainly many data we have, don't do that. Now, of course, the easiest way for me to change this is instead of doing 10 MERS, would be to do 20 MERS. Now I've dramatically increased the space of possibilities, and so the odds of having just statistical matches start piling up are very, very low. So that is certainly something that people do too. And in the case for the calculation we were doing, we just got lucky. We actually did not think 10 MER would be the right sampling for that data. We thought it would be a higher number, like a 15 MER or 20 MER. And it turns out the 10 MER was just actually spot on in terms of giving us this nice balance between sampling but statistical power that we could eliminate more common occurrences. All right, so we plotted the out degree. Again, a very useful technique. One should always do these basic, understand the overall statistics of one's data. We're doing the same cross correlation here that we did before, except since in that previous data set the value didn't store the account. That was a very fast read. We just had all the values were 1. Here we actually have a count, and so we don't really care that, we don't want it the case in this particular correlation. We don't care if this 10 MER appeared 10 times in this one sequence and it appeared 3 times in this other sequence, and when we multiply them together we get a 30. That's not really what we're really more interested in, how many unique ones did they each have? How many distinct ones did we each have? So we use the double logy function to basically convert all our numbers back to just zeros and ones and then do that correlation again. And then here we do and since the values don't matter when we do the cat key mul, we don't need to do that, and then we do the same correlation. And so here we are, we're finding the sequences with that have a greater than 8 match here. Actually doing some fairly inside tricks here to do that. You might ask, what is this put? So it's fairly clear what I'm doing here, right? I'm taking this count, and I'm saying please return the sub-associative array of all things with greater than a value of 8, more than 8 matches. All right, that's good. Then I'm flooring that. I'm saying make that all, just ones, all right? And then I'm doing this trick here, which is called put val, and I'm giving it this random string. Well, when I do that, so right now this is just an associative array without a value. When I put that thing in there, since all my things have a value of 1, and I'll have one string, it's now saying, you know what, I've just made all those values tilde. I'm like, why on earth would we do that? Well, it's because when I AND them together, okay, we have to decide what mathematically, when we AND two associative arrays together, if you recall the lecture where we talk about these collision functions, we have to pick a collision function for the two strings, all right? And this key stores this pedigreed list, which I really want to keep, and this just shows me which ones are the high match, and I don't really care about that. Well, the default collision function, when in doubt, throughout deform, is min. So tilde is lexicographically after every other printable character in the alphabet. So when I do a min here, I'm just going to always return these values here. So there was only one entry greater than 8, and I ANDed them together. It then did a min of tilde with this whole string here, and it said, aha, C is less than tilde. I'm just going to give you the C, and so there we go on. So this is just a cute trick, but it's a way of sort of using the collision function and the group theory that we talked about in the earlier lectures to get a very nice, just selecting the one that I want here. And so that's what that does. And then there you can see, so of this sequence ID and this sequence ID, they had 8 matches, or greater than 8 matches, and this was the exact 10 MERs that actually matched. Okay, and then we can go back before and look up those two sequences, compare them side by side in the original data, and then we see these were the actual positions here. And you would probably look at these. Well, what do we think here? Well, 137 and 138. That's right. 139, 140, 141, and then jumping all the way to 149. So it looks like those guys are all part of one long group. But then 60 and 172 and 130 are probably isolated 10 mers. And then over here, what do we have? We have 111, no, but we do have 119, 120, 121, 122, 123. So that's probably also a bigger group match. And so you probably, in fact, those all line up with this. They're except for the 149 here, but actually no, some of them match, some of them don't. So they're each part of a larger piece, but not necessarily overlapping in the same. They aren't contiguous with each other, and that's the kind of thing that people who do this, then really look at. And of course, a real match would be more like something with many more sequences. This is all just randomness and things like that. So, all right, so that's the demo. I want to thank you, and again, next week, tell your friends who maybe who weren't here today that is the one lecture. If you had to come to one lecture in this entire class, I didn't tell you that at the beginning, you noticed, right? Because then you would have skipped the other 7. But no, it'll be what we've done before will really make that a lot easier. That's the real one, and you will then be able to go, when you leave that lecture, run all those examples on those test databases that we have there from your LO Grid accounts, and have all that kind of fun. And then really, and we really want you to do that, because we've released D4M on the web. We need people to test it. It's much better if you guys find the issues, and then we'll just make it better. And likewise, it's a step towards you guys actually using the technology, and then in your actual for your actual application. So, thank you very much.